let's do. See if we can't remember. Oh, sorry. See if we can't remember what the products of these reactions, these addition reaction of alkenes would be, right? So take a minute and see if you can't predict what the products of this particular reaction would be. Bromocyclohexane, yep. Okay, and so how I'm going to do this for all these reactions that we're going to study is I'm just going to color the carbons on either side of that double bond, right? Because what we're going to see is, again, these are addition reactions where we're going to have something being added to either side of that double bond. All right, and so in the case of HBr, what's being added to one carbon is a hydrogen, and what's being added to the other carbon is the bromine. All right, and it's not a bad idea to get in the habit of sort of drawing out both of them. But in this case, if I switch to the positions of the hydrogen and the bromine, let me just do that real quick. All right, is this a different molecule that I've drawn here? In this case, these would be the same thing, right? If I just take this molecule and like flipped it, rotated it 180 degrees, I'd have the exact same thing, right? So in this case, it would just be one product. You can pick whichever one. That would be my product here. Okay, the other thing is I will explicitly draw in that hydrogen, but of course it wouldn't be wrong to just have it like that as well, right? Because we don't explicitly draw our hydrogens. In this case, since we're adding a new bond, since we've just created that new carbon-hydrogen bond, I'm going to get in the habit of drawing it, but if you didn't have it there, that would be perfectly correct as well. Okay. This is what's called a hydrohalogenation reaction. Hydro, because you're adding a hydrogen on one carbon. Halogenation, because you're adding a halogen onto the other carbon.
Is our test going to be on paper?
Yes. Yeah, a lot of drawing, right? Yep. Okay. This is again what we're, same as we're going to see for all of the reactions of alkenes. This is an addition reaction, specifically of HX, where X is a halogen. All right, chlorine, bromine, or iodine. Fluorine is also a halogen, but it just behaves a little bit differently from the rest of the halogens because it's so electronegative. It tends to have like slightly different properties. So we're not going to lump it into the same category here. Okay. So in the case of cyclohexane, if I gave you these two reactants and said, what's my, or I'm sorry, cyclohexene, if I gave you those two reactants and said, give me the product, boom, done and done. Okay. With regard to these reactions, and there's going to be like a little something special that we're going to have to learn about each one of these reactions that we cover. For this one, these reactions have what's called Regio selectivity. Okay. And it gets this fancy name, and I'll sort of explain what this is here in a second, but it's named after the individual who sort of discovered this. This is what's called a Markovnikov addition. All right, so what the heck does that mean? Let's take another example. All right, again, we're going to start with an alkene. So this would be propene. All right, again, I'm going to color the carbons on either side of my double bond. And now I'm going to add my hydrohalogen. Just for the sake of mixing it up, I'll pick a different one here. Okay, HCl. All right, but in this case, if I drew my two products, my two possible products, right, one where the chlorine goes on the red carbon, and another where the chlorine goes on the blue carbon, I get two different products. All right, these are no longer the same thing because I picked a different choice of alkene. It's no longer like nice and symmetric, so I get these two different products. Okay, and it turns out that this one, this first one, is our major product. All right, so if I asked you to draw me the major product of this reaction, you would only include this structure here. All right, and so how do I know that that's my major product? Because this is what's called a Markovnikov addition, where that bromine is always going to go on the more substituted carbon. Right? So that's what a Markovnikov addition is. We get the Br on our more substituted carbon. Does anybody remember what the heck I mean by more substituted? We had these special terms for these carbons depending on where they were in a molecule, right? Primary, secondary, tertiary, that is the degree of substitution of that particular carbon, right? So this one here, this is a secondary carbon. This one here, this is a primary carbon. The bromine's going to go on whichever one has that higher degree of substitution, right? The bromine goes on the more substituted carbon. So I'm going to look on either side of my double bond. I'm comparing a primary carbon with a secondary carbon. Okay, secondary is higher, it's going to go on that secondary carbon. Okay, if you remember at the beginning, we kind of like randomly learned how to designate carbons as primary, secondary, tertiary, and I was like, trust me, we're going to need that skill when we start learning about reactions. So this is a perfect example here, right? We got to be able to look at a molecule and say, all right, what is the degree of substitution? Because in this particular reaction, whichever carbon is more highly substituted, that's where the bromine's going to go. Okay, so let's just practice a few more here. Make sure we got this down. All right, everybody take a second and give me the product of these two reactions. All right, so for this first one here, remember we got to figure out which one of these carbons is more highly substituted. I guess just to be clear, how do we go about determining the degree of substitution? We're going to count how many carbon-carbon bonds, for example, this red carbon has. So that'd be 1 carbon neighbor, 2 carbon neighbors, 3 carbon neighbors. So this one's a tertiary carbon. For my blue one, it's got 1, 2, so this would be a secondary carbon. All right, so then which one of these carbons is the iodine going to go on? The tertiary, right? So in this case, my red carbon. Okay. Kind of move this over. Boom, boom. Oh, it's not BR. Whoops. And again, you don't have to put that hydrogen if you don't want to draw it explicitly. Importantly, though, it would be incorrect to put the iodine on the blue carbon, right? Again, we want to put it on the more highly substituted carbon.
So it would be a dimethyl and not a methyl, the red bond.
So it's actually just one methyl group, because then the other one is the iodine itself, right? So this is a carbon-iodine bond, and then this is a methyl group right here. Yeah. And I guess let's just, I said Br on the more substituted carbon. It's really the halogen, whatever the halogen is. Let's say X for our halogen. All right, then for this next example here, in this case it is a bromine. Is that bromine going to go on the red carbon or the blue carbon? The blue carbon, because the blue carbon's secondary compared to the red carbon, which is primary. So again, that's how I'm going to do these problems. I'm going to go and say, all right, well, this one's on the end, so it's a primary carbon. This one's a secondary carbon. It's going to go on whichever one has the higher degree of substitution. So in this case, it's going to go on the blue, and the hydrogen will go on the red. All right, let me give myself a little bit more space.
You do say that double bond disappears, right?
That double bond disappears, correct. We don't really talk too much about mechanisms in this course, but it turns out that in this reaction, it's this pair of electrons from this double bond that's actually like reaching out and grabbing that hydrogen and forming that new bond. So it's that pair of electrons in that double bond that's like actively participating in that reaction. All right, so then for this example here, I'm going to go through and is my red carbon primary, secondary, or tertiary? Secondary. And what about my blue carbon? It's also secondary. So now I have a tie. So now there's no preference for one carbon or the other, right? The bromine wants to go on whichever carbon's more substituted. In this case, there's not going to be any preference because they're both secondary, all right? Not only that, but unlike that very first example that we did, if I put the, in this case, it's a chlorine on my blue carbon, I'm going to get a different structure than if I put that chlorine on the red carbon. Right? One of them's 2-chloropentane and the other one's 3-chloropentane. I don't have enough room. I'm gonna have to scrunch this all in here. Drawing too big. Right? So in this case, which one would be my major structure? Well, there's not a preference for one or the other. I would actually get a 50-50 mixture of these two different products. Right? So in this case, you would have to include both of these structures. They're distinct structures. Right? Again, this one would be, if we wanted to name it, 3-chloropentane. And this one would be 2-chloropentane, right? So they're distinct structures. Both of which have that chlorine on the secondary carbon, so I'm going to have to include them both as products of this reaction.
So we don't need to include the hydrogen?
No. No, again, because it's like this reaction is creating that new carbon-hydrogen bond, I'm going to draw it in there, but no, you could just leave it off. And a lot of textbooks you will see it left off, right? Cool, okay. So again, this is this hydrohalogenation where we have an addition of HX, where X is a halogen. And for this one, our little special thing to consider is the Regio selectivity of this reaction, what we call a Markovnikov addition, where the halogen goes on whatever the more highly substituted carbon is. All right. Okay. So now take a minute and predict the products of this reaction. All right, so now, because I'm using Br2, I'm going to get a bromine that's added to either side of that double bond. All right, this is what we call just a halogenation. So again, an addition reaction of now a diatomic halogen, addition of X2, where X is again Cl, Br, or iodine. All right, and for this one, because you're adding the same thing to either carbon, there's no sort of regio selectivity to be concerned about, right? It's the same thing going on either carbon, okay? But this reaction does have what's called stereo selectivity. It's what's called an anti-addition. All right, so this is only going to be sort of relevant when we're talking about a cyclic alkene that we're starting with. So for example, if I start with cyclohexene, right, so I'm going to get a chlorine on either side of my double bond. That stays the same. Okay, so I'll just put those in. All right, but I'm not quite done here. Remember, with these rings, we have both these cis and trans stereochemistry conformations that we can draw. And since this is an anti-addition, that means that one of those chlorines gets added to one side, so it gets the wedge, and the other one gets added to the other side of this ring, so it gets a dash. So an anti-addition means that the X is going to be added to opposite sides of the ring. Which really just means that we're always going to get the trans stereoisomer. Bless you. And again, this is only something we have to worry about for cyclic alkenes. All right, so then take a minute and predict these products for me. Bless you. All right, so let's do this bottom one. This one's actually pretty straightforward here. Do I have to worry about Markovnikov in business at all? Right, so it's going to be a bromine added to the red carbon. It's going to be a bromine added to the blue carbon. I don't have to worry about what to put where, right? Is it a ring? No, so I don't have to worry about that stereochemistry business either, right? So I just have to make sure to stick a bromine on either side of that double bond. Right? Nothing really crazy for that one. Now for this next one, all of a sudden I got a ring here, so I do have to worry about the stereoselectivity. Okay, so if I start by sort of just redrawing my original molecule here. Whatever, you just got to make sure they're pointed on opposite directions, right? So if I draw a wedge for this blue carbon, in this case it's iodine, I need to make sure to put it on a dash for my other carbon. All right. Now, for this one, for this carbon right here, if my iodine is on a dash, I need to make sure to put the other bond at the other type, right? So in this case, that existing methyl group is going to have to become a wedged bond, right? It's got to be pointed in the opposite direction there. All right, but importantly, anti, so my iodines are on opposite sides. All right, so then just one more to practice this. All right, so importantly, I just have to draw those two chlorines pointing in opposite sides. So if I'm going to put this one on a dash, I need to make sure to put this one on a wedge. All right, and then I'm going to just move this. And that means I got to make this ethyl group now into the other type of bond, which would in this case be a dash. So you could have also given me sort of the exact opposite, where your ethyl group is on a wedge. Either one of these would be acceptable. All right, again, the important feature is that these two chlorines are on opposite sides. All right, and then sort of just to be clear, why do I have to make this one into a dash if this one's a wedge, right? Looking on this carbon here, why did I have to make that ethyl group a dash when I made that chlorine a wedge? All right, if we take a molecule, you can never have 2 wedges. Oh my gosh. This would be illegal. Okay. If we did another one where we then had dashes, 2 sets of dashes, this would also be illegal. All right. Any carbon can have 2 straight lines, 1 wedge, and if you draw 1 wedge, the other one has to be a dash. This is the only sort of acceptable way of drawing those bonds on a single carbon. All right, so because I made one of those bonds into a wedge, I had to make the other one into a dash. All right, so then our last reaction. Now is going to include not just a halogen, but also in the presence of water. All right, it's a little bit more difficult to just kind of intuitively predict the products here, so I'm just going to sort of show you. So if we have a halogen in the presence of water, we get a bromine added to one side of our double bond, or a halogen, in this case it's a bromine, and an OH added to the other side. This is what's called a halohydrin. This product here, where you have a halogen and an OH group. So these reactions are called halohydrin formation reactions. Again, an addition reaction of an OH and a halogen. And our special considerations for this one is this reaction has Regio selectivity. All right, it's also a Markovnikov addition, specifically with respect to that OH group. The OH goes on the more substituted carbon. All right, so if instead of doing 2 butene, I did 1 butene, everybody take a second and predict me my products here. All right, so where am I going to put that OH group, on the red carbon or the blue carbon? The red carbon, because it's going to go on the more substituted carbon, which means that my halogen needs to go on the blue carbon. All right, so similar to our hydrohalogenation reactions, we're going to have to think about the Regio selectivity, making sure to put the OH group on the more substituted carbon. All right, but these reactions also have stereoselectivity. They are also anti-additions. So again, if I have a ring, everybody take a second and draw me my products here, my product here. All right, and just like we saw with the last reaction, because this is an anti-addition, if I'm going to put one of those functional groups, the iodine, on a wedge, I need to put the other group on a dash. All right, they need to be added to opposite sides of that ring because this is an anti-addition.
Doesn't matter which is the solid or the bond, as long as they're opposite.
Correct. Yeah, it doesn't matter as long as they're opposite. All right, so then we can do another example that kind of rolls both of these into both of these considerations together. All right, so what if I had my methyl cyclopentene, 1-methyl cyclopentene, and we'll do, what haven't we done? All right, so I'm going to be sticking a Br on one carbon and an OH on the other carbon. Where should the bromine go? On the blue carbon or the red carbon? The blue, because that red carbon needs that OH group, because the red carbon is more substituted. Not only that, but this is a ring, so I'm going to put one of them on a wedge, doesn't matter which one I choose. But importantly, then that other group has to go on a dashed bond. And what am I going to do to this methyl group here? I got to make it the other type. So in this case, since I drew a dash, this has to become a wedge.
There's another product that could have been come out of that.
You could have drawn where like dashes and wedges were exactly flipped.
Right.
So if all of your wedges were dashes and all of your dashes were wedges, that would be perfectly acceptable as well. Importantly, the OH group must go on this carbon, and these two must be pointed in opposite directions. Those are the two features your product would have to have, or it would be wrong. But again, if compared to what I had, just to draw it to be clear, if you had drawn, oh my gosh, this is going to be all sorts of running out of room. If you had drawn it like this, with the methyl group on the dash, the OH on the wedge, and the bromine on the dash, that would also be okay. Yeah. All right, so keeping track of these reactions is like kind of a notoriously difficult part of any organic chemistry course. So I highly recommend that you guys start a stack of flashcards, right? I mean, we're going to be just learning various reactions. The best way to do it is to sort of flashcard these, to have that as a way to sort of quiz yourself. So for example, for the ones that we learned today, if I'm building flashcards, on one side I'm just going to have something like HBr, right? And I want to know what HBr does. We're going to have a lot of different reagents that we've learned. Thus far, we've only talked about alkenes, right? But of course, we're going to introduce more functional groups and more reagents. So keeping track of all that is going to be important. So starting now will make your life easier, right? So if on one side I have my reagent, my HBr, on the other side I'll say, okay, this is what converts an alkene to what we call an alkyl halide. I'll have like a little bit of an example reaction going on. And then maybe a note that this is a Markovnikov reaction, right? Sort of setting up your flashcard where on one side is your, what we call the reagent, right? And on the other side is all that important crap that you want to know about it can sort of help you out. And so then if I'm practicing, I have this deck of flashcards. One of them's HBr, the other one's just bromine, and then another one is bromine and water, right? These are the three reactions that we learned about. Then when I'm studying, I can just draw a random alkene, pick up, go through my flashcard deck and say, all right, what's this one going to do? Draw my product. All right, what's this next one going to do? Draw my product, right? You can sort of study these on your own. You obviously have your OWL online homework, right? But you can also sort of go about, you should be able to draw any alkene and tell me what the product would be with any of these three reagents. Okay, so you want more practice problems, just draw 5 different alkenes, start drawing from your deck of flashcards saying, okay, what is this reaction going to do? What's the product of this reaction, et cetera, et cetera. Okay, anyways, starting on this deck of flashcards before we learn too many of them, right? There's going to be like, all of a sudden it's going to get real overwhelming if you start on, chapter 7 trying to build a flashcard deck. So starting now will sort of make your life a little bit easier keeping these straight. All right, any sort of course is more of a marathon than a sprint, meaning that if you keep a good pace throughout with the material, you're 10 times better off than trying to cram everything in the weekend before the exam. I understand the natural college student instincts to save everything until the last minute and try to cram it in. Trust me, it does not work nearly as well as pacing yourself throughout the semester, right? Each week we learn about a new stuff. Make sure you got that buttoned up before the next week. It's just going to make your life easier. Okay, so again, my big recommendation, start that flashcard deck early. Cool.